Hey, what's going on, guys? Against here. Last video we implemented our tree node class, and the instances of the tree nodes, literally the game tree nodes, the building blocks of for the game tree we're supposed to be creating during the Monte Carlo tree search. And in this video we're going to be defining the Monte Carlo tree search class itself, and also we would be defining the methods within this class, and in the later videos we would be implementing these methods one by one to make it clear of what kind of action every single method takes there. So the very first thing I would like to do is to define the Monte Carlo tree search class. So class definition here, and I want to create the class called Monte Carlo tree search, and the very first method to implement would be the method to search for the best move in the current position. So let's call it dev search, and it would be taking the self instance followed by the initial state. And now a few words about the initial state. What is this and how exactly we're supposed to be making use of it? So the initial state is whatever board position we want to find the best move for. That's kind of it. So it doesn't obviously mean that this is the very first empty board state. Just call initial state from the terms of Monte Carlo tree search algorithm. And within the search method, the very first thing to consider, we want to create, well, actually initialize or create a root node. And in order to do this, we need to say self.root equals to, and I'm creating the instance of the tree node now. I'm passing the initial state as the first argument, so this board position that we're supposed to be looking the best move for. So this board position, and we just need to find the best move for this position. So this is the first argument, and then the second argument would have been none, because tree node takes the second parameter. It's kind of the parent node, if any available, basically. And after this, we need to walk through the famous, well-known 4 phases of the Monte Carlo tree search algorithm that are known as the selection phase, just to select the node, expand the node, expansion phase, then the simulation phase, and finally the backpropagation phase. It's far easier. It's easier to implement and to make use of it rather than to explain, well, at least for me. So I would rather be focusing on the implementation here rather than the explanations. And in the very first video within this series on reinforcement learning tic-tac-toe game, there is a link to a fantastic video by John Levin, who is given the lecture on theoretical backgrounds of the Monte Carlo tree search algorithm. So make sure to watch that if you're unfamiliar with this algorithm. So the next thing to consider, there might be 2 scenarios in terms of limiting the search capabilities. So we can either limit the number of iterations. So one iteration involves like selection, expansion, simulation, and backpropagation. So as far as all these 4 actions are being done, that's the one iteration. So the one way of limiting the iterations would be to make the fixed number of iterations within our Monte Carlo tree search. And another way of how to proceed would be to set a time limit. And let's say we have like 1 second limit, and there would be some number of iterations that we are capable to do within this time frame. And that would be the exact number of iterations that we'll use in order to find the best move. So both are applicable, but I would be using the fixed iteration approach because it's just easier to deal with. Well, actually, implementing the time limit is trivial as well, but I just want to keep this fixed iteration because, I don't know, it's more didactic probably. So here, the next thing we want to do, we want to search, let's say 1,000 times, 1,000 iterations, or better not search, or let's better say walk through 1,000 iterations. So I can simply say for iteration in range 1000, and I don't know, maybe like more noobs way of calling this like make search 1000 times. I don't know how to call it. Well, anyway, and here the very first thing to consider, we need to select a node, and that's it basically. So node would be equal to self.select. We don't yet have this function, but we'll define this quite pretty soon. And in order to select the node, we need to pass the root as an argument, so self.root here. And then the next thing to consider, well, regarding the expansion, regarding the node expansion, it would be the matter of distinguishing between the whether the current board position is terminal or non-terminal, and depending on that, we would be either expanding node or getting the best node using the UCB formula, UCB1 formula, or maybe it's a slight modification. Not sure what am I supposed to be using in particular. So if we have a terminal node, we would be using this UCB1 formula, and in case if this is a non-terminal, sorry, not the non-terminal, if it's fully expanded, then we're going to be using this UCB1 formula to pick up the particular node. Just don't really want to say about this now. The time would come when it comes to implementing that specific method. And on the other hand, when it comes to if the node is not fully expanded, in that case would it be expanding the node, so, and that would be the exact place for the expansion phase. But for now, the next thing to consider would be to actually get the score for a current node. So we want to score current node, and this is the simulation phase. And this is the selection phase. So the simulation phase is done the following way. So we're creating the score variable, and we say self.rollout, and rollout is again like another Monte Carlo tree search specific term. So there are two kinds of rollouts, so-called light and heavy rollout. So the light rollout is a random play, while heavy rollout might have involved some more complicated algorithms to get the score for a current given board position. But again, like for tic-tac-toe, light rollout with a random self-play is more than enough, so we'll stick with this, at least in this series for now. And when it comes to embedding neural net to evaluate both the probability of whether this move is worth to be done or not, and the winning probability for a current given move, we'll drop the rollouts completely, because we would be using the neural network to get the score for our move. But I didn't yet work that out that great, so it's not yet time to talk about that. But just wanted to give you the further idea, an idea of the further approach within this project. So in order to make the rollout, we need to send node.board. So we need to send literally the board state of whatever node we've picked up, and depending on the iteration, this node might be completely kind of different node in particular. So we would be expanding nodes every next iteration, because, well, I think why this would be happening would come more clear during the next videos, basically. Okay, so getting the score, and finally we need to backpropagate the number of visits and score up to the root node. So no matter how many nodes we have, let's say we have this root node, some nodes here, some nodes here, so say we are here, so we backpropagate into the parent, and from the parent we're backpropagating to the root node. So I hope that's clear. And here we simply say self.backpropagate, and we're passing the node itself and the score. And finally when we have walked through all the all the iterations, we need to actually return the best move. So we want to actually pick up the best move in the current position. So I will enclose this within the try except statement because there won't be moves for either drawn or won position. So that's the simple way of how to avoid the error there. But anyway, we want to return, and we'll use the method like get best move. And it would be, we need to pass the self.root, and we also need to pass the value for so-called exploration constant. And it would get more clear when it comes to implementing this get best move method, but just a quick teaser regarding what this constant is. So we would be so there is a well-known trade-off between the exploration and exploitation in Monte Carlo research algorithms. So the idea is that on the one hand we want to pick up the move that we've searched for, and we have some information about, and we know that this move is relatively good. And on the other hand, we need to we want not to miss some promising opportunities. So by using some knowledge that we already did obtain from the search, this is known as the exploitation. And when it comes to looking for some better opportunities, this is known as the exploration. And there is a constant that is present in the some sort of an equation we're maximizing in order to get the best move, and the value of that constant actually allows us to alter the behavior of the selection logic. So by increasing this exploration constant, we can make our algorithm, we can force it to more like picking up the some moves, some nodes that you don't really have that the search doesn't really have that enough knowledge about, but it would be trying to get some new data. And on the other hand, if this constant would be kind of less than like if we minimize the value of this constant, it means that we would be more like relying on the available data. And when we want to return the best move, so why was I talking all of this stuff? So when we want to return the best move eventually from the search, this means that we have explored everything we could explore already. So we're setting the constant equal to 0, and this means that we're not kind of exploring anything, we're just making use, we just want to exploit the data. So it would be a little bit more clear, I hope, when it comes to the equation itself, when we would be implementing this get best move, probably in the next video. So I would be using the fixed constant of 2, as suggested by John Levin in his incredible lecture, but the constant of 2, exploration constant of 2, would be used in case when it comes to when it would be working within these iterations, when we actually really want to explore some hidden opportunities. But when it comes to getting the best move, we actually set this to 0, so we completely rely on our exploitation, not exploration. Okay, so, and also we need to say accept and pass, and that's kind of it. So now the very last thing within this video, I just want to define this methods that has been involved within the search method itself, and we'll start with this select. I'm not going to be implementing them, just define them, not to forget what we're supposed to be doing in the next video. So the first method, we want to select, well, let's say most promising node, like this, and def select, it's taking the self instance as always and the node. And again, like this node might not always be the root node, because Well, okay, I would better leave this for the videos to explain. Just pass here. And the next is the rollout, I guess. Yeah. So the rollout means we want to simulate the game by making random moves until reach end of the game. Okay, so def rollout, and it takes the self instance and the board state as an argument. So remember, like this node.board would return the tic-tac-toe class would return this board class from our tic-tac-toe game. Okay, and then backpropagation, let's say get results, and here I would rather say this backpropagate the number of total wins, of total visits and the scores up to the root node through all the nodes being encountered within the game tree. So it's not obviously being backpropagated to the root node immediately. It might be backpropagating first to some parent nodes and then to their parents and then eventually to the root node. But anyway, we end up this backpropagation within the root node, which is important. So def backpropagate, and it takes self and the node to backpropagate the values for and the score as well, and we pass here as well. And last but not least, method to implement would be this get best move. So I'm just trying to check whether I did define the methods correctly. Well, it seems like. Okay, so the very last thing to consider, we want to, well, it calls like get the best move, but what it is in essence is actually, it's the matter of we want to select the best node select the best node basing on, well, for now I will call this UCB1 formula. I'll show this formula later on, well, probably most likely in the next video when it comes to the implementation. And maybe I would change this to what is known as UCD, which is a specific application of the general UCB formula. So sorry guys, I'm very new to this stuff. So one problem is I don't clearly understand this for 100% on my own, and trying to explain this, it's even more complicated. But well, let's actually keep this UCB1 formula for now. Okay, and def, let's call it get best move. Well, more likely to call this would be probably like get best node, but in order to avoid getting confused here, it's better to call this get best move. So what it takes the self instance, the node, and what is known as exploration constant that I was trying to explain kind of already. Okay, I think this is it. So probably the one last thing to consider is just try to run this tic-tac-toe in the terminal to make sure that my Monte Carlo research class is error-free. So Python 3 tic-tac-toe.py. Yeah, and this is the output from the previous part. So, well, I really hope that it's gonna error-free here. Just make sure. Oh, it won't show any errors until I create the instance. Okay, so let's try to create the instance. like this. Yeah, it still doesn't give me an error, unfortunately. Well, okay. If any errors there, it would show me later on. So anyway, I will be running these methods one by one to show you the exact functionality of each one. Well, at least as far as I'm capable of doing that. Because, you know, like if you just implement all the methods and just make this Monte Carlo research algorithm running for current given position, yeah, it obviously would give you the best move. But for me personally, it was quite pretty unclear, like why exactly this is working actually. So I will try to show, well, at least this get best move method in separate. So I'll just try to create a couple of nodes and call this get best move to give you an idea like what would be the difference. Okay guys, so I think this is it from my side regarding this tutorial in particular. Again, I'm really sorry for being such a dumb noob in this, both Monte Carlo research in particular and machine learning stuff in general. I'm just learning this myself. I'm learning this on my own at the moment. It's much more complicated compared to web scraping that I was doing really a lot on this channel. But again, like you probably, some of you might know that my ultimate goal is to create a completely, Monte Carlo research plus neural network based chess engine, and that's the ultimate goal for me. But first I want to try my skills and try to learn something using this tic-tac-toe example. So thanks for following, thanks for your attention, don't take it too serious. CodeMonkey King was with you guys. Until the next time, and take care.